Hello everyone, this is Mrs. Logus and welcome to your first pre-calculus flip video of the year. You're going to be hearing either myself or Mr. McConey almost every night. We're going to be making these videos to prepare you for class the next day. And the way that the class is generally going to work is you're going to be coming in, hearing the topic from the video. We're going to be doing warm-up questions that reinforce the material, and then you're most likely going to be working together to hear the material for a third time. So the reason I really liked this flipped course is you're really hearing the material 3 different times per day, which I think will help it sink in for sure. So I look forward to going on this flip journey with you. I know it's different for a lot of you, but based on past years, I feel like in general, it ends up being a pretty positive experience. So I hope the same for you. So what I'd like to call your attention to first is if you could please make sure to have your Unit 1.0 notes packet out in front of you. You're going to be taking notes along with me in this first video. And something I want to bring to your attention is this should look like the very front of your packet. And the reason I want to bring this up is that even though there's not a ton of space here and all the definitions are already typed for you, just because something's already typed for you does not mean that we want you to just skip over it and not read it. In fact, the opposite is true. When Mr. McConey and I type something out for you, that means we do really think it's important, but don't necessarily want to take time on the video because sometimes it's review material. Like in front of us here, you have such things as equivalent fractions, adding and subtracting, like denominators, all things you're aware of, but we're trying to remind you of. So make sure you're reading those along with taking the notes on a daily basis. For today's lesson, though, we're going to be focusing on real numbers and their subsets. And at the bottom of this page, I don't have it all here, but that's where you define different types of numbers like natural, whole, integers. But I'm going to go through it anyway with examples. So if we look first at this list of numbers, our goal is to figure out which ones are truly natural numbers. But first, before we get into which ones are which, let's define what a natural number is. So down here where it says name the characteristic, you should have a space as well. A natural number is really defined as a counting number. And if you think about it, as when you were very young, when you first started to learn how to count, you usually used your fingers to start. So I'm going to make a little note here that usually used your fingers to start counting. So usually you started with the number 1. And so natural numbers are really counting numbers, so you start with 1 and go up from there. 1, 2, 3, 4, 5, and etc. So in another thing I'm going to write down at this point is the natural numbers are the smallest subset of numbers that we can possibly have. So what I'd like you to do is take a look at these numbers A to P, and I would like you to write down which numbers in this set you think are defined as natural numbers. So I'm going to pause the video now and I will come back with my answers. So please pause your video here. So from this large subset, the numbers that I had to be natural from 1 and above were the numbers 1, 3, 12, and 1,503,456. Nothing else on the list was defined as a natural number. So what we're going to keep doing is building our real number system, because everything we do in pre-calculus, everything we do in your past math classes is based on how we define numbers. That's why this is our first section. The next subset is a whole number. And in terms of a definition or a characteristic of a whole number, in my opinion, a whole number is really your natural numbers plus the addition of the number 0. So it really is every number you've already said is natural, and then really just add in the addition of 0. So with that said, I would like you to pause the video again, and I will come back in this space with which numbers I would define as whole. So make sure you're including past subsets when you do that. So please pause the video now and write down what you think is true. So notice that I kept the same colors. The whole number system is first the inclusion of all of the natural numbers plus the addition of 0, which I put in a different color. So these numbers in this set will be defined as whole numbers. As we keep growing, the integers involve more numbers. The integers, if I come down here, are really natural numbers. The addition of whole numbers, so which is really 0, and then it really includes the addition of negative natural numbers. So what I would like you to do is, without me defining any more, I would like you again to write down in this space above which numbers you think will be defined as integers with the addition of negative natural numbers. Again, make sure to write all the numbers that are already included from previous subsets. So please pause now. So here's my list of all numbers in the set that would be considered integers. First, again, I considered, let me color code. First, we have our natural numbers. Then we have the addition of 0 for our whole number set. Now, again, whole numbers doesn't mean just 0, it means this and above. Then these two is what I would consider negative natural numbers. So they're counting numbers, but on the other side of 0 towards the negative side. So again, they're still counting numbers, and I will make that note down here. They're still counting, but they are negative now. So I'm going to write down these are the addition of the integers. As the subsets continue to grow, we get into rational numbers. And from your algebra and geometry days, especially geometry, when you see the word rational, I want you to focus on the word ratio. And if you remember the similarity unit from geometry, when we were comparing different quantities, or saying one triangle small, one triangle large, and we're comparing them, we wrote ratios as something like this. If one side length was 3 and one side length was 4, we wrote it as a fraction. Or you could write it as 3 is to 4 as another possibility. But a ratio really does lead towards numbers that could be written as a fraction or compared as a fraction. And so if I wanted to define a rational number, it is a number that can be written as a fraction. And yes, just like the previous ones, it does include all the previous subsets. It does include natural numbers, it does include whole numbers, and it does include integers as well. So because all of those could be written as a fraction, which we'll be talking about in a little bit. So again, I would like you to pause the video, look at the subset, write anything you think could be defined as a rational number based on this definition down here. Okay? So please pause now. Okay, so my set was rather large here. I had all of my natural numbers first because, remember, all of these could be written with a denominator of 1. 3 over 1, 12 over 1. My whole number could be written as 0 over 1. The integers could be written as negative 7 over 1. And I'm guessing that a lot of you wrote all the answers in red. A lot of you probably wrote all 5 of these fractions because they were written as a ratio. But it's possible that some of you forgot that these numbers, even though they're written as decimals, could be easily changed to fractions. So I'm going to be talking about 2 ways or multiple ways to determine if something is a fraction if it's not written like that originally. So if I come over here and I write 3.14, how do I know that that could be written as a fraction? Well, think placeholders. I have 3.14. And the 1 and the 4 are in the tenths and the hundredths place. So if I wanted to rewrite this as a fraction, because my decimal goes to the hundredths, this is really 314 over 100. And so because it has exactly 2 places, I can easily rewrite it as a fraction. And both of these numbers can be divisible by 2. So a more reduced version of this fraction would be 157 over 50, or 157 fiftieths. So this is for sure rational. Also, 0.12345 zeros and a 1 also can be written as a fraction because, again, think about placeholders. Behind the 0, or behind the decimal point, we have 1, 2, 3, 4, 5, 6, 7 placeholders. So this could be rewritten as 1 over 1, 2, 3, 4, 5, 6, 7 zeros, which would really be 1 over 10 million. So this can decently quickly be written as a fraction, so I know it is also rational. Now, as a quick aside, Something I've learned in my past classes that I thought I'd share with you is how to change a decimal into a fraction, specifically if it's a repeating decimal. Like, for instance, in this subset, what if I had given you the number 2.3 repeating, and I'd ask you if that was rational or not? Some of you probably wouldn't know, or you'd quickly try to grab your calculator to find out, which we'll talk about in a minute, but some of you might appreciate the way that this was originally founded to possibly be a rational number. So, remember, 2.3 repeating really means 2.33333 and so on. And so a method that I've learned to see if this can change into a fraction is the following. If I don't know what something equals, or if I want to somehow make an equation, I generally want to set it equal to a variable that I like, for instance, x. So if I say that x equals 2.3 repeating, whatever I do to one side of this equation, I can do to the other side. So what if I wanted to multiply both sides by 10? Above this, it would become 10x equals, well, the reason I wrote this over here is if you multiply 2.3 repeating times 10, what you're really doing is move the decimal over 1 to the right. So this really becomes 23.3 repeating, because the 3's still carry on forever. And what I noticed, the reason I wrote this line underneath, is if I decided to combine or subtract these two quantities, 23.3 repeating minus 2.3 repeating, the 3's repeatings would cross out, and we'll be left with 21 equals 10x minus 1x, or 9x. So if I divide both sides by 9, I get that x is 21/9, and if I divide that both by 3 to reduce, I get 7/3. Now, I purposely picked this example because if you look at your subset here, 7/3 was an option, so that's why I picked 2.3 repeating specifically. Back to one more thing, if you're ever not sure, if you don't remember this method, which is okay, and you would like to plug this into your calculator, feel free to press math and then enter. And if your calculator is able to change this into a fraction, you know it's rational, and if it keeps it the way it is, 2.3 repeating, or is not able to change it, it is not rational. Speaking of not rational, another subset of numbers is irrational. And what I already wrote here is it would make sense that the definition of an irrational number is something that cannot be written as a fraction. And I also wrote down decimals that never repeat and never end. So for instance, if I had like 0.12457852331, and notice there's no repeating going on or anything, that would be considering a irrational number. So feel free to pause if you want to write any more of this down. But I'm going to go back up here, and I would like you to write down which numbers you think are irrational. So please pause now. So you can think of, again, irrational numbers as everything that is not rational. And because everything else on this list was rational, the only options were square root of 5 and pi. If you want to check yourself and plug them into your calculator, notice that when I did that, the decimals never repeated and never ended. So that's why I consider them irrational. The last type of number is a real number, and I've already written the definition for this as well. A real number is really anything that's not an imaginary number. And everything we've talked about so far is considered a real number. So I wrote all numbers in the above set are real. To remind you what an imaginary number looks like is something with an I, like 2i is an imaginary number. You might remember doing the quadratic formula and getting something with imaginary numbers. So really anything with an I next to it is the only thing that's not considered real. The last thing I want to leave you with is this Venn diagram. Not the prettiest, but I hope it'll help. This Venn diagram that helped me learn the real number system. In the real number system, we started small with natural numbers, grew to whole numbers, grew to integers, then anything in here could be written as a fraction or rational. Then we learned that there are numbers like square root of 5 and pi that cannot be written as a fraction, but all of these together make up the real number system because none of them have imaginary numbers. So for those of you that are visual learners, this might help you. So we're going to end our first video. Thanks for sticking with me, guys.